All right, let's do more practice with solving systems using matrix exponentials, because I know it's quite a difficult topic. And so in particular, let's solve x prime equals ax with initial condition 3, 2, using matrix exponentials, where A is the matrix 1, 1, minus 2, 4. And as usual, it all boils down to finding the eigenvalues and eigenvectors. So the details you can find in the notes. So step 1, 2, 3. The eigenvalues. So if you do the determinant of A minus lambda I trick, it's lambda equals 2 and lambda equals 3. And then for the eigenvalue 2, you get the eigenvector 1, 1. And for the eigenvalue 3, I believe you get the eigenvector 1, 2. And remember, what that tells you is that A is PDP inverse, where D is the matrix of eigenvalues, so 2, 0, 0, 3, and P is the corresponding matrix of eigenvectors, so 1, 1, 1, 2. So here for 1, 1, we need lambda equals 2, and for 1, 2, we need lambda equals 3, because that's how we chose our matrix D. And then remember to find e to the at. The beautiful fact is you just need to do e to the dt. So p e to the dt, p inverse. And then remember e to the dt, you just do e to the eigenvalues. So 1, 1, 1, 2. And then that's another fact that we covered. So e to the 2t, 0, 0, e to the 3t, and then 1, 1, 1, 2. 1, 1, 1, 2 inverse. Inverse, and remember how to calculate that inverse. So for 2 by 2 matrices, 1, 1, 1, 2 inverse is 1 over the determinant. So 1 over 1 times 2 minus 1 times 1. And then you flip the diagonal entries. So 2, 1. And you do minus the anti-diagonal. So minus 1, minus 1. Again, that's just for 2 by 2, by the way. So don't try it on higher order matrices. And here the determinant is 1. So in the end, we get 2 minus 1, minus 1, 1. So going back to our matrix exponential, this thing, then we get 1, 1, 1, 2, e to the 2t, 0, 0, e to the 3t, and then 2 minus 1, minus 1, 1. And then we get 1, 1, 1, 2. So you multiply the first row by e to the 2t. So 2e to the 2t minus e to the 2t minus e to the 3t. And then e to the 3t. And then you just cross multiply. So I think you get, in the end, 2e to the 2t minus e to the 3t. And then minus e to the 2t. So minus e to the 2t plus e to the 3t. And then 2e to the 2t minus 2e to the 3t. And then minus e to the 2t plus 2e to the 3t. And once again, the beautiful thing is to now find the solution. So step 5. Solution, you can directly multiply this matrix by the initial condition, which I like to remind you was just 3 and 2. So it turns out it's precisely 3 times the first column 2t minus e to the 3t, 2e to the 2t minus 2e to the 3t, and then plus 2 times the second row. So minus e to the 2t plus e to the 3t, and then minus e to the 2t plus 2e to the 3t. And again, this is precisely because the beauty of matrix exponentials is you just multiply e to the at by the constant vector 3t. And then you can simplify this. So this becomes, if you want, 6e to the 2t minus 3e to the 3t minus 2e to the 2t plus 2e to the 3t. And then 6e to the 2t minus 6e to the 3t minus 2e to the 2t plus 4e to the 3t. And after the dust has cleared, this becomes 4e to the 2t and then minus e to the 3t. And then let's see, 4e to the 2t and then minus 2e to the 3t. Let's see, is that correct? Yeah. And again, optional if you want. You can write this as e to the 2t times 4 plus e to the 3t minus 1 minus 2. So once again, what are the steps? Find the eigenvalues, eigenvectors. Do this trick with pe to the dtp inverse to get a matrix. And then for the initial condition, you just do first initial condition times first column and second initial condition times second column. And that's all she wrote.